If I take a loop also, the magnetic field will be going in and out because this will be the magnetic field. If there are n number of turns to the solenoid, that much amount of current is being passed through this particular solenoid. That is written as mu naught into n into L into I. If two current carrying parallel wires in which the currents are in the same direction, the forces will be such that they are attractive in nature. Hey all, I'm Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence. And we were discussing about moving charges and magnetism. So let's continue on to that. So today we are going to learn a new law called as Ampere's circuital law, or simply Ampere's law. So what Ampere's law actually states is that the line integral of a magnetic field B is equal to mu naught times the net current enclosed. What Ampere's circuital law actually states is that the line integral of the magnetic field will be equal to mu naught times the net current enclosed by that particular path. So what it actually looks like is that integral, that is a closed integral B dot dl will be equal to mu naught I. So this is the equation that states Ampere's circuital law. And you might have seen that it is line integral. We have seen surface integrals for Gauss's law, just like that, just similar to that. We have Ampere's circuital law in magnetism, and we can say that just like surface integral was chosen there, here we are choosing line integrals because we are considering small line elements. There are different types of integrals. There are volume integrals, there are line integrals, there are surface integrals. All these become more relevant as you choose a course which is more relevant for that. Like if you're choosing engineering or higher order physics, mathematics and all that, then these sort of integrals will be more convenient and will be more understanding for you. Right now, just know that this particular integral, that is a closed integral, is a line integral of the magnetic field, and that will be equal to mu naught times the net current enclosed. So this will be net current enclosed in that particular conductor. So to make it even more clear, if we have a current carrying conductor like this, let's say this is infinitely long and it is going like that, and the current is flowing upwards. So current is flowing upwards, then we can say that we can actually use the right hand rule. So if we place the thumb in the direction of the current, the curls of our finger will indicate the direction of the magnetic field. So we can say that this will be the magnetic field B. So in order to state this in a mathematical form, we can use this Ampere's circuital law, which states B dot dl is equal to mu naught I. So one more thing, this will be concentric circles, as the field will lose its strength as it moves away from the source material. That is one thing you have to remember. So this is all about Ampere's circuital law, and we'll look at some applicational stages where we have to find the magnetic field of certain materials. So first, let's consider an example of a long straight current carrying conductor. So current is passing through this, and that particular current is I. So if I amount of current is passing through a long straight conductor, what will be the magnetic field of that particular conductor? What will be the magnetic field? It is emitting. So that is what we are going to find out today. We looked at the cases where what is the force experienced by a long straight current carrying conductor when it is placed in a magnetic field. Now we are going to look at what is the magnetic field of this long straight current carrying conductor. So we know that the magnetic field produced will be like this, and we are going to find that out. Using Ampere circuital law that we just learned, we know that integral B dot dl, that is closed line integral B dot dl, is equal to mu naught into I enclosed. Okay, that is the Ampere circuital law, and this is the equation representing the Ampere circuital law. So after this, we are going to take a look at what are the different terms here and how we can find the magnetic field due to a straight long current carrying conductor. So when we apply the integral sign, we'll get integral dl, that is B into integral dl. Here the angle between them is considered to be 0, that is this is a dot product. So we can say that B dot dl is equal to B cos theta dl or B dl cos theta. Here we are considering that that particular angle is 0, that is cos theta or theta is equal to 0 degrees implies cos theta is equal to 1. So we are not considering the cos factor, that is the angular factor here. So we can just say that integral B dl is equal to mu naught I. So integral B dl is equal to mu naught I. And again, upon integrating this particular quantity, we will get B into 2 pi r, which is the circumference of a circle, that is this particular wire. Then we can say that 2 pi r is equal to mu naught into I. Or simply rearranging this particular equation, we can say B is equal to mu naught into I divided by 2 pi r. And this will give you the magnetic field exerted by a straight long current carrying conductor. It will be equal to B is equal to mu naught I divided by 2 pi r. It is very simple. Just so you don't have any doubts, we are considering a small line element here. Let's say dl, and that will be in the direction of the loop, and the magnetic field here also is in the same direction, which means they are parallel to each other. That is why the angle cos theta is equal to 1 and theta is equal to 0 degrees, just so you don't have any confusion. Whenever we consider a small line element, that is in this particular case dl, we are considering that particular small line element. And if we zoom in the wire is basically cylindrical in shape, and that is why we have 2 pi r also. So don't have any confusions, just learn it in a simple sense. We have the Ampere circuital equation which states that B dot dl is equal to mu naught I, and upon integrating we can say that B into 2 pi r is equal to mu naught I, and simply rearranging we can say that B is equal to mu naught I divided by 2 pi r, which will give you the magnetic field exerted by a particular wire which is carrying current. Now we are moving on to something a bit more complicated, but basically very simple, because the mathematics is very simple. The concept is a bit tricky to grab. So we already know that if we have a current carrying loop, we have a magnetic field going inwards and coming outwards. That is, if I have a particular loop, let's say this particular loop is carrying a current, which means if I take this out, make it three-dimensional and turn it to its side, I can say that current is going in like this, which means if I push it into this board, I can say that current is going inwards like this and it is coming outwards like this. So this magnetic field is going inwards and the magnetic field is coming outwards, which means the magnetic field is going like this. That is, the magnetic field around this will be circular in nature. Just like if we take a long straight current carrying conductor, the magnetic field will be in circles. Just like that, if I take a loop also, the magnetic field will be going in and out, because this will be the magnetic field. The magnetic field also will be in a circular loop, which means that at one point it will be going in, at one point it will be coming out. If I have a conductor like this, that is, the curve is like this and the other half is on the other side. So it will be going in and coming out, which means the magnetic fields are like this. Okay, if current is going in and coming out, if this is the nature of that particular current carrying loop, I can say there will be a magnetic field in circular loops, and this is the representation of that particular loop. And if I have multiple loops like this, very close by to each other, I can say that So if I have multiple loops like this, so let's say this is a wire which I have bent in the shape of a spring. So this particular loop is carrying a current. Let's say I amount of current is passing through this particular loop, which means that it has a magnetic field, and each loop will have a magnetic field on it. That is, here there will be a small magnetic field like this, here it will be a small magnetic field, here also there will be a magnetic field, here there is a magnetic field, here there is a magnetic field. There are several fields, and the field will depend on which direction the current is flowing in. Not just above, below also there will be fields like this. So if the current is flowing like this, the field will be going in this direction, like this, like this. Let's say this is the direction of the magnetic field. The point is that if I only had a single loop which was carrying current, then the magnetic field would have been like this. Okay, if this is the direction of the current, then this will be the magnetic field around that particular loop. If I have a number of loops, there will be a number of magnetic fields around that. Not only there, but we already saw that if I have magnetic field going in like this and coming out like this, this will be the nature of magnetic field lines. You have already seen this in your 10th standard also. If you have magnetic field like this, if there is a current carrying loop, that is, if there is a current carrying loop, the magnetic field will be like this. It will be passing almost linearly through the center, and towards the edges it will be bending off. It will be diverging. Now, if I place one more magnetic field coming in and out like this, what they will do is that they will try to bend this back and make it into a straight line. So if I place another loop like that, they will try to bend it and make it into a straight line like this, which means these magnetic field lines will be contained within that particular loop. So if I have multiple loops like this, what will happen is that the magnetic field lines will behave something like this. That is, at the center, they will be strong, and the magnetic field lines will be more concentrated in between those two magnetic fields, or within the loops, the magnetic field lines will be flowing through much more strongly. And outside, it will be comparatively very weaker, but inside the magnetic field lines will be very strong. The point I wanted to make was that this is how the field lines bend and form a stronger magnetic field inside the loops. I don't want to make things more complicated for you. So simply, if I have a spring-like shape like that, that is called as a solenoid. So this is known as a solenoid, where a conductor is being bent into consecutive spirals, and that particular shape is known as a solenoid. And now we have a current passing through that particular solenoid. Let's say I amount of current is passing through that solenoid. So this particular solenoid, when current passes through that particular solenoid, it will behave like a bar magnet. That is, it will have a north pole and a south pole. Depending on where the current is entering, which direction the current is going, there will be a north pole and south pole. For example, so the magnetic field lines will be more stronger in the center and weaker towards the outside. This will be the shape. And there will also be magnetic field lines around the loops also, which we just explained. The magnetic field lines will be looped around every loop like this also. But the point is that this will be the general shape of magnetic field lines of a current carrying solenoid. Now what we have to do is that we have to find what is the magnetic field of this particular current carrying solenoid. For that, what we do first is that first we list down all the things that we know. The first thing we know is that we know I amount of current is passing through this particular solenoid. So we know I amount of current is passing through the solenoid, where I is the current passing through, and we also know that this particular solenoid has a length of L. So we know L is the length of the solenoid, and we know that N, capital N, is the number of turns per unit length. That is, N is equal to N into L. That is, number of turns per unit length. How many turns are there per unit length? So we can write it as N into L. That is, number of turns into length will give you number of turns per unit length. And this much is all we need in order to find out what will be the magnetic field of that particular current carrying solenoid. So we start from Ampere's circuital law, which states that integral B dot dl is equal to mu naught I. Now here we have to remember a couple of things we have studied. That is, current flow is nothing but the flow of charges, and the charges flowing through a certain length can be calculated using other quantities. Like, if I amount of current is flowing through here, I can also say that if there is n number of turns to the solenoid, I can also say that the current flowing through this particular solenoid can be written as mu 0 into n, mu naught into ni, or simply I can just say that integral B dot dl can be written as mu naught into n into L into I. That is, this much amount of current is passing through this particular solenoid. NL is nothing but the number of turns per unit length, which is written as NL. So, which means that if there are n number of turns to this solenoid, that much amount of current is being passed through this particular solenoid. That is written as mu naught into n into L into I. So here, in order to find out what is the magnetic field of this particular solenoid, we have to consider one more thing, which is known as an Amperian surface. I told you when I said that Ampere's law is very similar to Gauss's law, because just like in Gauss's law we consider Gaussian surfaces, in Ampere's circuital law we consider Amperian loops. It can be circles, like for the straight current carrying conductor, we choose an Amperian loop like this. It was circular in shape. Here we are going to consider a rectangular shape. That is, we are going to consider a rectangular shape like this one, and we are going to name it A, B, C and D. So what we are going to do is that we are going to find out what is the magnetic field in that particular area. So for that, we will integrate this from this particular limit. So this particular limit is nothing but our closed surface, and we are going to find out what is the magnetic field in that particular closed surface. So we can say that integral B dot dl of A, B, C, D, A is equal to mu naught n into L into I. So this ABCDA, I am going to split it into its components. That is, integral B dot dl ABCDA can be written as integral A to B integral B dot dl A to B plus B to C integral B to C B dot dl plus integral C to D B dot dl plus integral D to A. So we can say that if I want to find out the integral of this particular closed surface, I can also write it as individual quantities like this. I am going to calculate what is the integral from here to here, here to here, here to here, and finally here to here, which means I'll come through this closed surface individually and find out what is the net magnetic field. So luckily for us, it is very simple to do. Why? Because if this is the direction of the magnetic field, this particular AB, that is, this particular AB is perpendicular to the magnetic field, which means that this AB and DC, that is, integral A to B B dot dl is equal to integral d to c B dot dl is equal to 0. Why? Because cos theta here is equal to 0 because theta is equal to 90 degrees. The angle between the magnetic field and this particular dl element is now 90 degrees, which means that integral B dot dl or B dl cos theta is equal to 0 degrees, which means this particular A to B term is 0 and this particular C to D term is also 0. So two terms are already exterminated, which means that we only have to worry about A to D and B to C. Now you're worrying about integral A to D, that is integral B dot dl A to D, A to D. So we are worrying about the integral B dot dl from A to D. This particular length is what we are worrying about right now. But you don't need to worry about that also, because this is also luckily 0 because the magnetic field beyond or outside the loops or outside the solenoid tends to be very weak, which means that the field inside the loops or inside the solenoid is the only factor we are going to consider here. So we can say that integral B dot dl is also 0 from the distance A to D because it is really far away from the center of the solenoid, which means the magnetic field will be very weak. Here the B factor is 0, which means that also becomes 0. And finally, we can write that integral B dot dl from where to where? Only B to C is existing. Integral B to C is equal to mu naught into n into I into L. So we can write it as integral B dot dl is equal to mu naught into n into I into L. Here the angle between the magnetic field and the line element dl is nothing but 0. So we can simply write BL is equal to, that is BDL, integral BDL is equal to mu naught into n into I into L. And finally, when we integrate this particular line element, that is this line element from B to C is nothing but the length of the solenoid, which is L. So we can say that we can write this particular equation as integral B dot dl will become BL because we are integrating from B to C where the angle is 0, which means cos theta is equal to 1, which means theta is equal to 0 degrees. And finally, B to C is nothing but the length of the solenoid, which is L. So we can write B dot dl is equal to BL. So we write B into L is equal to mu naught into N I L. The L's get cancelled and we can write B is equal to mu naught into N into I. So this is the magnetic field of a current carrying solenoid. Maybe it seemed like it was too much, but I'll explain it again. It is very simple to do. So what we have to do is that first we have to consider a current carrying solenoid, and we have to consider the fact that it has a length of L and number of turns as N. Then what we are going to do is that we are going to apply Ampere's circuital law, which states that integral B dot dl is nothing but mu naught I. And instead of just I, we are going to write mu naught into N into L into I. Why? Because there are N number of turns and N is nothing but N into L, that is number of turns per unit length. And we can say that the number of turns which is across this length L is N into L. So we can say the current passing through that will be N into L into I. So we get the term mu naught into N into I into L. And finally, upon integrating through a closed surface, we need a closed surface to integrate. We considered a closed surface, and when we started to integrate, we split the terms into 4 components, that is A to B, B to C, and C to D, and finally D to A. And from here we understood that since AB and DC are at an angle of 90 degrees with the magnetic field, we don't have to consider them. They automatically become 0. And since this particular AD is very far away from the center of the solenoid, the magnetic field there is very low. So we can say that that part also becomes 0. And finally, only the B to C part remains, which is within the solenoid, which is passing through the center of the solenoid, and BC is nothing but the length of the solenoid. So upon integrating, we can say BL is equal to mu naught into Ni into L. So here the angle between magnetic field and the length element is nothing but 0 degrees. So we can say cos 0 is nothing but 1. And finally, we can write B into L is equal to mu naught into NIL. L's get cancelled out. We can say that B is equal to mu naught into Ni. It is as simple as that. Now what we are going to consider is the fact, what is the force experienced by two current carrying conductors which are parallel to each other and the current is in same direction. So what will happen to those current carrying conductors? Imagine that we have two long, straight, infinite current carrying conductors like this, in which current is flowing in the same direction for both of them. If current is flowing through these conductors, that means that there will be a magnetic field developing. We know that the magnetic field developing will be in this particular shape, that is concentric circles. Magnetic field will be developing, and the direction of the magnetic field depends upon the direction of the current. In this particular case, current is going like this, which means the magnetic field is given by the right hand rule, and this will be the direction of the magnetic field. And similarly, here also there will be a magnetic field. If there is a magnetic field and there is a current carrying conductor, we already know that a current carrying conductor kept in a magnetic field will experience a force, which means that if, let's say, this is wire A and this is wire B, then wire B will experience a force because of the magnetic field produced by this particular A wire. That is, let's say this is the magnetic field produced by wire A and this is the magnetic field produced by wire B. Then each of these two wires will experience a force because of the magnetic field produced by the other. So wire B will experience a force on it because of the magnetic field BA, and wire A will experience a force because of the magnetic field produced by wire B. So both of them will experience a force, that is clear, and our job is to find out what is the nature of this particular force and what is that force. So we already know that the equation to find out the force on a current carrying conductor is nothing but F is equal to L into I into B. Given that the angle between them, that is L and B, is nothing but 90 degrees. We are considering the fact that the angle between the magnetic field and the length element is 90 degrees, because if you are taking line element DL like this and this is the direction of the magnetic field, we can say that they are at 90 degrees to each other. That is why sin theta is not considered there, and we can just say that the force experienced will be equal to L into I into B or B into I into L. We already know this from where we found out what is the force experienced by a current carrying conductor. So we can say that the force experienced is equal to L into B into I. Now, this is not just for one wire. Each of these two wires will experience an individual force, which means that there will be a force experienced because of wire B and there will be a force experienced because of wire A. So force experienced due to wire A and force experienced by wire B. So two forces will be experienced. Let's say L is the length of the wire and let's say IA is the current flowing through the A and IB is the current flowing through the B wire. So for B it will be IB and here it will be IA. And the magnetic field is the external field, not the internal field that particular wire produces, but it is the external field in which that particular wire is kept. For example, this particular B wire is kept in the influence of the magnetic field produced by the A wire, which means the magnetic field experienced by wire B is because of A wire. So this particular external magnetic field is BA and here it is BB. So the equations are set. Let's say this is equation 1 and this is equation 2. So this is the force experienced by two parallelly placed current carrying long infinite wires. Is it that simple? No, of course not, because we also have to have a definition for the magnetic field. Lucky for us, during Ampere's circular law, we already proved that, or we already found out that the magnetic field due to a current carrying long conductor will be equal to, that is, B will be equal to mu naught I divided by 2 pi r. This we just proved in the, or we just found out in the Ampere's circular law. For a straight long current carrying conductor, we know B is equal to mu naught I divided by 2 pi r. Here we are going to substitute that particular equation in this formula, which means that I can write this as F is equal to L into I B into mu naught I A divided by 2 pi. Here R is the distance between these two. So I can say, let's say this is the distance, let's call it as D. Then I can say 2 pi D is the distance. Rearranging this equation, I can write it as mu naught by 2 pi into IA into IB into L divided by D. So I can say that this will be the force experienced by a particular wire kept near another wire which is parallel in nature carrying an electric current I. So the force experience will be equal to mu naught by 2 pi into IA into IB divided by D into L. Now, one thing you have to remember is that if the currents are in the same direction like this, the force experience will also be like this. This will be the force exerted by A and this will be the force exerted by wire B, which means that they are acting opposite in direction, which means they are an attractive force. If two current carrying parallel wires in which the currents are in the same direction, the forces will be such that they are attractive in nature. These two wires will bend in order to attract itself when the current are in the same direction. If the currents are in opposite direction, that is, if IA is in the opposite direction, what will happen is that the force will be directed in the opposite direction, which means they will repel away from each other. So one thing to remember is that if the current is in the same direction, we can say that they will be attracted to one another, and if the current is in opposite direction, they will be repelled from one another. And the equation to find out that particular force they exert is F is equal to mu naught by 2 pi into IA into IB divided by D into L. So this is the force experience, and we can actually state what is amperes. That is, we studied that the unit of electric current is amperes, but we never defined what ampere truly is. You might have learned it in PUC first year, but we can also define ampere through this particular equation here. That is, we are taking the case of two long current carrying wires, right? So we can say the currents flowing through them are 1 ampere if they are kept at a distance of 1 meter, that is D becomes 1. This will be equal to 1, and the length also is 1 meter. Let's say this is also 1 meter. Then we can say that the length is also 1 meter. Then one more assumption has to be taken, that is, we know mu naught by 4 pi is equal to 10 raised to minus 7 Tesla meter per ampere, but here it is mu naught by 2 pi. So what we are going to do is that we are going to multiply a 2 here and a 2 here. So we can rewrite this as mu naught divided by 4 pi into 2IA IB, which means if two wires are kept like this 1 meter apart, which is having a length of 1, then the current passing through that wire is 1 ampere and the current passing through them is said to be 1 ampere. If you have difficulty remembering the sentence, just remember that the force felt between these two wires will be attractive when current is in the same direction, and if the currents are in the opposite direction, they will be repelled away from each other. And if it has a length of 1 and they are kept at a distance of 1 meter apart, and we fix the mu naught by 4 pi issue, then we can say that that will be the definition of 1 ampere current passing through. So just a reminder, the ampere circuital law is very important. We use it everywhere in magnetism. So we can say that B integral B dot dl is equal to mu naught into I enclosed. If we consider an Amperian loop, so this particular loop, closed loop we are considering is known as an Amperian loop. So the Amperian loop which we are considering, so the magnetic field of a long current carrying conductor can be found through considering an Amperian loop around that particular wire. If any conductor is carrying a current, we can say that if we consider an Amperian loop around it and we write the equation, that is closed line integral of B dot dl will be equal to mu naught into net current enclosed by that surface. For example, here our Amperian loop is in the form of a circle and the dl element is in the direction of the loop and magnetic field will be given by the right hand rule. So we can say that integral B dl will be equal to mu naught into I enclosed, or simply here dl or this particular Amperian loop is in the form of a circle. So we can say that B dl will become B into 2 pi r, which is equal to mu naught into I. So we can rewrite this particular equation as B is equal to mu naught I by 2 pi r. This is the magnetic field for a long straight current carrying conductor, which is derived from ampere circuital law, which stated that B dot or closed line integral B dot dl is equal to mu naught I enclosed. And in the case of a solenoid, again we considered a solenoid which is carrying a current. We considered a closed surface which one part is inside the solenoid and the other part is away from the solenoid, and we consider the fact that all sides which are at right angles to the solenoid will be equal to 0 and one is really far away from the solenoid. So the part outside of the solenoid is also 0. Only the part which is inside the solenoid will have a strong magnetic field, and we considered that only, and we reduced the equation to be B is equal to mu 0 into N into I. And finally, we also learned that if there are two current carrying wires in which the current direction is same, we can say that they will experience a force which is attractive in nature, and if the current is in opposite direction, they will repel away from each other. That is all. I'll see you again in the next class with more topics. Thank you.